How many people lost power this week where they live? Very few. Wow. Okay. Nice. How many people's place caught on fire? Good. That would be better. All right. Well, we're lucky that we're not missing too many classes. So I was gonna actually skip over the end of the last thing, but I feel like it'd be nice for you guys to know some of that. So I'm gonna finish that up and maybe just go over slightly more slowly some things I said. And then what this class is supposed to start with is to move from regression, which the whole course has been about, to classification. So, right, so we're, just to remind you where we were. So we had this, we introduced neural networks, these universal function approximators, and you can think of these just as a composition of regressions, where each one you pipe it through a nonlinearity before composing it with the next one. And so we also went through this algorithm, right, backpropagation, that was a way to think about a neural network as a graph computation, where we can sort of procedurally and sort of structurally devise a way to programmatically get the derivative that we need to do gradient descent for stochastic gradient descent. And then we move from these sort of fully connected things where every input goes into every node at the next layer to these more sparse networks called convolutional neural networks. And the idea there was, could we somehow get sort of more bang for the buck, maybe reduce the number of parameters while still getting really rich representation, and maybe using some of the intuition in devising these about what might work on images. And so mostly I went over, for those, the convolutions, working through the one-dimensional case, what that means, and then the two-dimensional case, and kind of showing you different filters and what they mean. But then, of course, the neural network actually learns those filters that you can involve with your inputs. So, and then I just mentioned that there are these pooling layers on top, so I'm gonna go back to there. But again, just to remember, like, the main thing I was telling you about were these convolution operations, where you don't have fully connected things here, you have instead these sparsely ones, and there's weight sharing by virtue of the fact that that filter gets applied at many, many different places. Okay, so, right. So basically, this is where we're at. Is we've mentioned these convolutional layers, and now I was telling you about pooling layers, which then operate after the convolutions by subsampling. And I give you a little bit of a flavor of that by showing you, like, if you were scanning for an eye or something like that. And so these two things together, the convolutions and the pooling, are kind of what we think of as the ability of neural networks to do feature extraction. And they can really only do a good job if you have a lot of training data. So, and so this is sort of one example of how a kind of typical architecture might work. So you might start, and again, most of these examples are thinking of the images. So the inputs here, even though you're used to seeing vectors, are actually matrices. And so sometimes you'll see this 3-at, and that's because they're thinking of like 3 channels for color images, but you can kind of just, I don't want to get into the detail of specifically how you handle color images, but let's just say they're just sort of RGB, and so you kind of extend things in a natural way. Right, and then feature maps, that's the sort of synonym for this word filter. And so you would define a priori some number, and maybe you would do cross-validation to find an appropriate number, right? And in the end, you're gonna essentially do cross-validation to pick a good architecture, and this is just an example of how you can combine different things together. So these things here, and then after you convolve each feature map with the inputs, then you would get sort of, oh, I see, sorry, Max, actually this is kind of complicated. But okay, all that is to say is you combine the convolution and some pooling, which we're gonna go into with more, and usually you alternate these, convolution, pooling, which does some sampling, then on that output of that you do more convolutions and more pooling, and you might sort of flatten it out, and then at the very end maybe have this fully connected layer. So in some sense, one way you could think about that is all this here is this feature construction with the convolution and the pooling, and then at the end, the fully connected layer is kind of saying, whatever feature you learn, now I'm gonna do like linear regression or something like that. And so in a sense, like, it's all the stuff leading up to that that's doing these fancy, complicated things that give them the rich power that they have.
So you learn those features afterwards?
You mean the things that we convolve with, these filters?
So first of all, we have the center point, each of these layers, and at the end we have an output classification. But the model is too big and we have a lot of trainable parameters. So later on, we're going to put in a small device, we don't have so much computing power.
Yeah.
Is there any way to learn those features so we can have less layers, just give the same output?
So So, well, there's two answers to that. So the things that are really computationally expensive are typically training the model. This is what can take weeks on even very expensive hardware. And once it's trained, it's much, much cheaper just to run stuff, to execute. So
we have a lot of maintenance costs after it's trained. We have all
so after it's trained, so there are people who try to do this like with dedicated hardware. So you might have heard like from Google, the tensor processing units, for example. There's other things you can do that are beyond the scope of this course called like model compression or distillation, where you try to distill the essence of a large, well-functioning neural network into something more compact. It's actually kind of a very open, interesting research question because it turns out you can do that, but you have to be very careful about how you do that. And that sort of relates to earlier last class when I said, if you have this, or if you have a universal function approximator with one hidden layer, then why are we ever doing more? And I said this is to do something with optimization. So it turns out you can leverage the benefit of the optimization that emerges when you have deep networks. And once you've done that, then you can more easily actually train a shallow network and things like this. But yeah, but that's a bit beyond the scope of this course. So typically, you can train them pretty well, and the only reason people want to compress them is to put them on like small devices like out in the world. But if you're just using it on a computer, then it doesn't generally matter for deployment. Right, so, and as I said, after the convolution, we push through a I don't think I said this, we also push it through a nonlinearity, just like with the regular neural networks, and it's a similar reason to before, because convolutions are a linear operator, so if we don't pipe it through a nonlinearity, then we're composing a series of linear operators, and then we all just end up again with one linear function. So it doesn't bias anything to add depth unless we add the nonlinearity in there, this thing we sometimes call the activation function, and we went through different ones last time, right, the sigmoid, and we said the ReLU was one that's commonly used, and so that's also typically used here. And so just as an example, maybe this is the input image, and you have maybe two different filters that you get an output by doing the convolution operator with one filter to get this, with another to get this, and then you would apply the ReLU there, which is the nonlinearity. And then after that, that's when you start doing this pooling thing, where you alternate convolution pooling, typically. And it's not like it's a hard and fast rule, these are just things that tend to work and they kind of make sense if you think about them. So I showed this last time, assume the filter is like an eye detector, and if you want to make that eye detector robust to the exact location of an eye, then you maybe want to apply that filter a whole bunch of places, right? And then just pick like the max of those. And that would be max pooling, and it would just be responsive to the highest response of the filter, rather than using all the filter responses that you get. So these pooling layers, this shows you an example here. So imagine this is after you've applied a convolution and you get maybe that sort of like an edge detection or whatever the neural network has decided it wants to do at the moment. And then what you do in pooling is you reduce the size of the convolutional output, and it could reduce it by different amounts depending on the parameters. But in this case, this is like, for example, a max pooling. But for each red square here, it takes the max and then puts it in the next output layer. And so in this particular sort of schematic example, you go from, I don't know what this is, maybe it's 20 and 20 to 2 by 2. So that's the sense in which it's making it much smaller. And you can also imagine that if in one of these red squares, imagine it like it applies this eye filter a whole bunch of places, then if it sees it at least in one place with enough confidence, then it will get the same response here, right? Because of the max operation. And so it gives you this sort of builds in these invariances to small translations in the features. And that's sort of one of the main reasons that we use it. And this is just like another example, like you can go through these more slowly on your own just to actually see, like in this case, right, it's the max of each of these. So the max of this is 6, you get a 6 here. Max of these is an 8, and so on and so forth. So nothing complicated. You might ask, does anyone know how we so everything I'm gonna tell you about how to compose different architectures needs, remember, to be able to use backpropagation and to take derivatives. So can anyone think about how, can we take a derivative through the max? It ends up, you can think about it at home, but basically you end up just pushing it through the one that ended up winning the max. And then the other ones it falls out of. So, but you can go home and think about that as an exercise. right? Okay, so and that's sort of the final, this is, you can see the size of the images here, right? So the convolution leaves the image roughly the same size, the nonlinearity leaves it exactly the same size as the convolved image, and then if you do some sort of pooling like max, it could be average pooling, then you reduce the size like this, and then you keep going, and you might repeat that sort of structured architecture again. And so one thing just to, like, it's interesting to think about these things a little bit more offline, but I'll just point out one, for example, is that because you're pooling these things, that in these small ones here, that for a given number of pixels, it sort of touches, if you will, more pixels in the original input than something earlier on. And that's because when every time you subsample, you're kind of condensing information into fewer pixels from the original image. And so, okay, right, so we can use the gradient descent again with the standard back propagation, something, right. Okay, so there I even tell you about the max pooling, I'm ahead of myself. So right, and what, like, I don't frankly track all the latest and greatest architectures because it's not very interesting for me, but this is an example, I don't know from what year, but I guess if you follow the link. By the way, the links I put here are just to give credit to the people whose images I'm stealing. They're not necessarily meant as robust references, although occasionally they might be, but don't assume that if I put a link in a slide that I think they know what they're talking about. But you should always credit where you're stealing your images. So, right, in this example, there's a little legend here, right? So there's like convolution layers, max pooling layers, fully connected layers, which, as I said, are usually just at the front, or the top, sorry, here. And that's because this is, again, like you think of all of this together as some crazy machine to do feature extraction, and then you kind of just sort of do linear regression or something relatively simple. Okay. So, and this is just, it's just kind of neat to see how things are changing in the field. And this is from, it looks like 2016, so it's already 3 years old, but there's a legend here about the size of the blob is proportional to the number of parameters, and you can just see how you get, do you get a trade-off between accuracy and the number of parameters and things like this. So you can see these are like really, really huge networks that are very expensive to compute, but there's actually smaller ones that do better. And so people are constantly trying all the kinds of different things to win competitions and to make better products. So, what architecture do we use? So in general, you can think about this as you do feature construction, and as I said before, you can do cross-validation. So maybe you think of 5 different models or 10 different models, and you pick the best one based on the holdout error, or the cross-validation error. But sometimes you might want to kind of borrow from another network, and in fact, this happens very frequently in neural networks. And I would say before deep neural networks became common, this wasn't something you would actually see as commonly as you do now. So imagine someone has spent like a month of training time on some expensive computer with some massive data set, and they have a neural network that's really good for their task. And what you're doing is actually not that task at all. The question is, like, could you maybe benefit from something in that neural network? And in fact, it turns out you can often do that. And again, that's sort of related to the notion that in some sense this is doing feature extraction, right? And then the kind of last layer is using those features to do regression or classification. And so it turns out in many cases that all the stuff that goes into learning this stuff is more general than the task at hand. And so you can sometimes think of this as somewhat task independent, even though it gets trained in this sort of end-to-end manner, right? The way this is learned is in the context of a particular task. So it may be a little bit surprising that this is true, but what you can do is then give it another task with new data, and you basically initialize it, or you don't even move these weights. So you could fix these weights, and you could apply gradient descent only to update the weights here, or you could initialize these weights here and then train it from there, where then you're sort of bringing it to a particular basin of the optimization space. So, and this is essentially what we would call in the old days transfer learning. I guess they still call it transfer learning. And in a sense, what you're doing is you're taking knowledge that's encoded in the form of a model from one task, and you're transferring it to another problem. And in particular, this can be helpful if you don't have a lot of data for your particular problem. Then you might benefit from having tons of data that's not quite as related to your problem. So Right, and so just a common example of that is maybe for natural images where you might have some massive database of what we call natural images, like you may have seen a lot of these examples, just like dogs and cats and trees and houses and lecture halls, stuff like this. And it turns out that if you have a huge amount of that data and you train a neural network, you can often use that beginning of the network to kind of do good feature extraction for other tasks.
How do you visualize each of those weights at the very beginning?
So if you don't sort of steal from another network, it's a bit of a, you know, these used to be known as a craft to get neural networks to work. Like if there's like 5 people in the world who trained with Jeff Hinton who could actually make them work, that's no longer the case. So there's a few tricks of the trade, and like these are not, they're somewhat based in intuition theory, but for example, you want to minimize, keep the weights relatively small, and there's a number of theoretical reasons, pseudo-theoretical reasons for this, but one is actually just to avoid the dead units problem. Remember that if you use a sigmoid or even a ReLU, you can push into the zone of the activation that has no gradient. And if you have a big gradient, then you're more likely to jump into and get dead. And one way to reduce that from the outset is to initialize with relatively small weights. So there's some sort of standard recipes for how to initialize that are, I think most of the stuff in TensorFlow and PyTorch probably does that for you, but I don't know. Okay, so, and I didn't say this explicitly, but I implicitly referred to maybe this has to do with a bias variance trade-off. And that's because what we're doing is we're kind of using a huge amount of data, in some sense is gonna, from another problem, will help us to reduce the variance, right? Because data helps to reduce variance, but it's not quite the right data, so we get a bit of bias. And the scenarios in which it's helpful is when we reduce the variance more than we increase the bias. But we're not gonna go through sort of the detailed technical thing, that's just a bit of the intuition. And so you could kind of think about this as doing, imagine you were to do PCA on your data, and which doesn't look at the label, right? PCA just like finds the axes of variation, and then you can take like the top 10 principal components and use these as your new features of what was originally very high dimensional data. So when you do PCA, there is no label, right? This is inherently sort of unsupervised. And so you can kind of think here is unsupervised because you're not using the right label. Right. And also PCA is linear. So, and there's one other trick that is, and it's nice to know about these tricks, but it's also nice because it tells you that these things aren't as miraculous as people say they are. But so what if you're trying to do this transfer learning and it doesn't really work, and you don't have a lot of data? Is there something else you can do? Could you somehow take your original training data, which is pairs of X's and Y's, and get more data? So imagine, for example, we were trying to build a classifier for 6s, for all the digits, and like from 1 through 10, and they look something like this, so you get an image and you get a label. So how could I, and imagine there was no relevant data, there was no other network to steal from, all I had was this data, and then I had to build my network from scratch. Can anyone think of a way that I could, for free, get more data? Right, okay, so you can, and is that also what you were gonna say? Yeah, okay, so you guys probably heard this trick somewhere, or are you very clever? Could be either one. Right, so you could rotate it. You could take that 6, and you can rotate it at random or through some systematic grid. And the thing is that you and I all know that, well, that these are 6s, although I guess at some point it might not start looking like a 6, but if you want to be able to recognize a 6 in any orientation, then you would assign a label 6 to all of these. And so, like, you might think, does this really help? Like, how can this help? All I did is rotate the images. I have no new information. So why does this help? Does it help? Yeah, it does help, because that's what I'm telling you. So we call this data augmentation, and this is sort of another way to encode prior information. So what's the prior information I'm encoding? I'm saying that I, as a human being, have decided that we all agree that 6s are 6s no matter what rotation they're in. So I'm encoding my knowledge as a human being that they're rotationally invariant. And so, in a sense, if I had a network that understood that property already, then giving it this augmented data wouldn't help. But it turns out that these convolutional neural networks don't, like the simplest ones, and it'd be very complicated to make it rotation invariant, they don't understand that, and therefore the simple trick of augmenting the data by rotating it actually gives you tons more data, and you can do much better, and you're also robust to rotation. And so sometimes people do this in domain specific ways, like so there's some examples for dermatology about moving masses around on a like radiology slide. And so right, a way to think about this is you're injecting prior information, but in a kind of weird sort of hacky way, right? Like it's not like you're upfront stating in a technical manner what it is. You're just like, oh, I'm gonna rotate my digits or something like this. And you can use any transformation that's label preserving. And so this can be a bit of a game in different domains, is to say, well, in this particular domain where I want to build a predictive model, like what are the invariances that I could use to augment my data that are not encoded in the neural network? And in fact, this is so important that there are some state-of-the-art results where you don't get them and they will totally fall apart if you don't do this. But at least at the time I made this slide. That was true, I'm pretty sure it's still true. And it can be very sensitive to the type of augmentation. Okay, so back to architectures. So far I've said you can stack it, like I say compose, but this is the same as stacking the layers together. And you can do it with convolutions, you can do it without convolutions. And so this is, these are some results up to 2014, where you can see on this axis is the performance, where lower is better. And you can see how many layers were here. So these were shallow networks in 2010, 2011. Then people got to 8 layers in 2012 with something called AlexNet. Again, 8 layers, but they did something different, I don't know what. Then they get to 19 and then to 22. So at this point in time, in 2014, 22 layers is the state of the art. So is that because no one tried more than 22? Who thinks that no one tried more than 22? Okay, who thinks that they tried more than 22 but it didn't work? Who has an idea of why it didn't work? Just an intuition. Yeah?
I kind of think I know why.
Okay. Okay, all right.
My understanding is basically by the time you go that far back, the gradients go to near zero.
Right, so there's been a long-standing problem with the gradients, and the deeper, again, and I'll tell you a little bit about this, and again, depending on how many classes get canceled or not, maybe I can tell you more at the end. But right, so there's a big problem with the gradients, and this is this paper that introduced a solution to that I won't have time to go into today, but it does something very counterintuitive. And so what it is in, which one is which? I think this is the test error, and this is the training error. So down here, the training error should be lower than the test error, and it is. But what's weird is that as I add more and more layers, so I go from 20 to 32 layers to 44 layers to 56, the training error actually goes up and up and up. So can anyone tell me why that's basically guaranteed to not make sense?
Is that also the case that we normalize each batch after each layer?
I don't know the details of what they did here, but even with batch normalization, as far as I know, this still would be a problem.
The gradient wouldn't get that big after batch normalization.
Batch normalization did not fix all the gradient problems, and there's a lot of people who pick on it as a bit ridiculous, although it is very commonly used. So it's true that batch normalization can help, but it doesn't get you. It doesn't really get you past 22. You have to do something else there, which are these ResNets, basically. So ResNets are the thing that let you go bigger, but the thing that I want to emphasize here is like how and these are the sort of things you should be able to think of as someone who's studying machine learning and who may go on. It's like, how do I know for sure that this is wrong? Like, what intuitive argument can I give to myself that this is basically messed up?
It should overfit.
What's that?
It should ideally overfit if you add code. The training error should close the code.
Right, but okay, yeah, so that's true, but the answer I was looking for specifically is that basically each smaller network is like a sub-network of the previous one. So the 22 layer is some network, then to go from 22 to 32, I'm just adding more layers, and then I'm adding more. And I could always set all those parameters to just be identity. So at the very worst, the deeper I go, I can just make that deeper part map the identity, and so I should always be able to recover what was in the shallower one. So in terms of just representation, there's no way that I can, which means it's some weird problem with training, right? It just means the optimization is not working well. So I'm gonna actually skip over that. Right, and so we've talked a little bit about this, and one has to do with the activations saturating, and you can do this thing that people keep mentioning too, which is you kind of renormalize the data at each layer, which can help, but doesn't completely alleviate the problem. And you also just have an issue where the gradient is unstable, because as you go deeper and deeper, it's basically a product of many numbers, and this is just inherently very numerically unstable. And so if you're not careful, it's pretty easy to just end up with like 40% of your activations becoming dead. And basically you just completely lose out on the ability to use that. So it could be that actually some of them should be dead. Maybe like that's a good thing, but in general, probably 40% is not a good thing. And the deeper the network, the worse the problem. And that's why we saw people kind of pushing the envelope to 22 and then stopping.
Would quad precision allow you to use more layers?
Would what?
Quad precision.
Quad precision. I don't think, I didn't think it through, but my instinct is that it's not the precision that's really hurting you, it's just the inherent instability of multiplying the numbers together. So maybe that helps a bit, but I don't think that would fix the problem. Okay, so that's kind of, I wanted to at least get that far with neural networks before leaving them behind, potentially for the whole class. So I'm going to start on the next topic, unless there are any outstanding questions. Okay, so everything in the class has been regression. And so in regression, we're always making a real value prediction, right? Like you can think of this as like blood pressure or age or things like this. And the difference with classification, which probably you all know by now, but just to be very clear about it, is it's just predicting a discrete class, right? And they're not ordered typically, these classes. So maybe, I guess if you're predicting digits, you could say they're ordered, but we don't think of them as ordered. Or a cat versus a dog, for example, is obviously not ordered. And sometimes we talk about binary classification, where the problem is you decide between one of two things. And sometimes we'll talk about multi-class classification, where instead of just, is it a dog or is it a cat, is it a dog, is it a cat, is it a zebra, or like any number of things, arbitrarily large. And so one thing that's really confusing is one of the simplest and most widely used classification models is called logistic regression. But logistic regression is a classifier. It's almost like the way linear regression is the simplest regression model, logistic regression is like the simplest classification model, except for its name, which is not very simple to understand. Okay, so what's the difference between these? So right, again, with regression, we're trying to predict that as some features change, like what the real value response is, right? And so here, that's the response. Here, maybe this is blood pressure, and maybe this is a set of genetic features. In classification, we're trying to find like a decision boundary that separates these two discrete classes for binary. So maybe these are cats, and now the axes are different here, right? So here there's an x, or like, we projected it down to one dimension per slide, and this is the y, the like response variable, or the target variable. In classification, at least in this image, this is feature 1 and feature 2, and we're trying to find a line in space that separates them. And the label here, the y, is, if you will, denoted by a purple versus a blue. But that's the key game, right? In regression, you're trying to find this sort of curve or this line that properly maps from input features to the output. In classification, you're trying to find a decision boundary that cleanly separates, or separates as well as possible between classes. So how does the representational capacity, how do we think about it? So in regression, a more complex or a richer model class means that we can essentially get curvier and curvier lines, regression curves, right? So we saw originally linear regression, then we augmented it with higher order features and showed that it could, even though it's a linear model, it can still get curvy. And so similarly, and with a neural network, right, it can basically be arbitrarily curvy if you give it enough parameters. And then similarly in classification, the more complex you can describe the more complex a decision boundary you can describe, then the higher the representational capacity of that class of models. Okay, so what is this classification boundary? I've just kind of alluded to it schematically here as some line in feature space that separates your two classes. But in practice, it's actually like technically, it's where the evidence, like in terms of where, and we'll get there, where the sort of probability of each class is the same, if it's a probabilistic model. And it need not, but it could be that just describing that line with math might be the entire classification model. Although next class we're gonna see that that's not always the case. But for today, it will be. And you may do so implicitly, right? You don't necessarily think about what line am I drawing. Instead, you're gonna think about how do I use features and then make a decision of which class it is from which feature. So, and in fact, we might end up with something analogous to linear regression, which is a linear decision boundary. And that will be the level set of a line. So we'll make our way there. And right, but similarly, linear regression has the equation of a line for the regression curve. So you can, in some sense, they're very analogous, even though they're doing completely different things. So more formally, what do we have? We're gonna again be given training data, X and Y as we were before. It's just that these YIs now belong to one of, say, K classes, and often just two classes. And again, we're gonna featureize our data just as we might have with regression. And then we're gonna build a predictive model which for unseen data, ideally predicts the class Y from the features X. And so all the sort of same notions of training and validation and cross-validation apply here again. So the only real difference is just that the labels are categorical. So, right, we're talking about predicting the class, like sorry, I might be switching between T and Y. But so what does that mean exactly? So when we talked about regression, it's pretty obvious. You're predicting something in some space, right? If you're predicting blood pressure, then it's whatever the units are in that. But so if I'm predicting dog and cat, like there's no cat or dog unit, like what am I predicting, just an integer? So it could mean that, right? It could mean that my prediction is actually an integer that lies in the set of labels. But it could also be more nuanced. Like what else could it be?
True or false?
Say again?
True or false?
True or false? I think true or false would be kind of, it would, so right, I would say that's another way to describe it. That's still like just here I call them 1 through K. If you had only 2, it's 1 and 2, and you could just map 1 and 2 to true and false. But is there something else that might? That's a nice idea. What if you're farther away from that decision boundary rather than closer? So imagine if I, on that picture, like, actually let me back up. Where is it? It's pretty far away. What, like, should this point get the same prediction as this point over here? Does that make sense? Maybe, but maybe there's something better, right? And so what would be better? It would be this. It would be to predict the probability that it belongs to each class. Because this gives you some idea of the confidence, right? And we know that these systems are noisy. We know they're not perfect. So we want to somehow capture the certainty we have. And maybe some 6s look more like 9s than others, and they lie closer to a decision boundary between them than other ones. So this gives us more information. Okay, so right. Okay, so I'm trying to remember what was in my slide here. So these are just the two things we talked about. One is the prediction might be just an integer or like a true false or some discrete set of labels, or it might be a probability. And so I've already kind of given you the intuition for why that is, but you can even just think of this as like, imagine you're in a hospital setting and you're building like a predictive model for, should I do this treatment or not, or is it this disease? Like in this, I think here you can see the stakes are very high and you want to understand the information the model is telling you in the most nuanced way possible. And so really, I would say in general, you really do want to have that probability. Okay, so you might think, could we just abuse these regression models? Was there a question?
Yeah, so if the probability was in a continuous interval, then how is this different from actual linear regression?
Well, maybe the slide will help explain that. If not, ask me again.
Okay.
Right, okay, so basically it says, what if we use regression for classification? And so, for example, just like linear regression where we had the solution was ordinary least squares, and we just instead, normally when we did that regression, the target variable y was a real value, as was just suggested, but we could just use it with 0, 1, right? Nothing would actually break down. Like we could crank through, we could get the closed form solution for the weights. And so imagine the data looked like this. Imagine there was a yellow cloud and a purple cloud where each axis are the features. So it's just a 2-dimensional feature space, and the label is denoted by the color, yellow or purple. So if we did that, who thinks this is a good model, like for classification? Who thinks this is a bad model? Okay, it's a bad model because we can see intuitively there's a line that cleanly separates the classes, right? It goes like this. So what's going on? Why am I not getting the right line here? Can someone see why? It's written there, but basically, if I have a classification problem where the game is to separate these clouded yellow from purple, but I treat it as regression, then the regression is going to try to fit a line. It's not looking for decision boundaries. It's actually doing something else. And in some cases, such as this one, it's easy to find examples where it falls apart. It's basically trying to get the regression line to fall down here, and so it's tilting the line away. And that's because we've set up a classification problem as a regression problem. So hopefully that makes some kind of sense to you, and maybe when you go home and you look and you think about it more, like sometimes these things take a little while to digest. So I guess when I'm here, I'm going a little bit quickly. I'm hoping to give you the intuition, and then you digest it a bit more, and then it's homework and things like this. But so you can do it, you can crank through it, but it can go quite wrong. And so a classifier would have just done this. And so this is sort of a simple example of why you don't want to use regression. The other thing is that, regression is just kind of the wrong thing for classification. And there's also, in regression, you're basically trying to fit a line as closely as possible to the points, right? And if I make my model arbitrarily complex, I add more and more polynomial features, then at some point, it will go through every possible one of my training points as it draws out the curve. But when I do classification, I want a separating boundary that in some sense is far away as possible from both of them. So in this example, this is like the best one because it separates them cleanly, but there's actually infinite lines that separate these two clouds cleanly, right? But this is the one that in some sense is furthest away from both. And so this is somehow where we would be, if a point fell right there, we would really have no idea where it was, right? Like, is it red or is it blue? But if I put that green line maybe down here, which still separates the points, then you can argue that, well, it's actually closer to the red cloud, so that actually I should have been able to say red, so that's not where the decision boundary should go. And so that's completely the opposite of regression. So in regression, you're trying to make the points lie kind of on a curve, and in the decision boundary, you're somehow actually trying to get them as far away as possible. And you may not necessarily be able to do that in the original space you're given. So if you're just given two features, X, and you don't augment them with polynomials or anything, then it kind of is what it is, right? But part of the game there is to augment them in clever ways with polynomials or with kernels and things like this, such that you can actually separate them while still maintaining generalizability. So we need something other than regression, and we need a loss, which is going to reward the desired outcome. And so this was just a little sort of motivation to say, like, you can't just use regression. Having said that, there are things outside the scope of this course that are very, very complex models. These are very related to each other. I spent a lot of my research time on these actually, called Gaussian process regression, or in other fields, sometimes linear mixed models. They're related. And these are models where to do classification, it's so tricky to actually do training that you sometimes do just use them in their regression mode for classification, and you can do better than if you didn't. So there's no hard and fast rule in machine learning, but if you have a classification problem and you can use a proper loss and a proper model with a decision boundary, you should absolutely do so. But just to highlight that sometimes you do the wrong thing with full knowledge and it still helps you on a problem. But overall, there are lots of tractable classification models, and we should use them, and we're going to spend a lot of time now learning about these. So let's kind of work our way from ordinary least squares and linear regression to think about how can we change this to actually do classification and to get a decision boundary. Okay, so how could we tweak OLS to make it do a binary classification, for example? Let's say just 1 and 2. Can someone think of an example that might be helpful? Let's not talk about the loss yet. Let's just talk about the model. So right now, this model, it takes the input features x, and it takes some weights that we're going to learn, and it produces an output. And as I change the w's and the x's, this output lies on the real value line, right? So there's nothing here that's constraining it to be here, nor is there anything constraining it to be a probability. So something is off, so I need to do something. So what's the sort of most obvious thing I might do, and this is actually what they did in the old days. You might have heard of something called the perceptron, which is sometimes taught in different versions of the class. I'm not going to go into it, but you basically take the sign of that thing. So if w times x is bigger than 0, then you belong to class 1. And if it's less, then it's class 2. This should just be 1, 2. So on this side, I'm just doing binary. But right, so if it's more than your class A and less class B or class 1, class 2, whatever you want to call them, right? That's just a label we're giving them. There's 2 classes, that's all that matters. And if you're completely undecided, meaning that you get a 0 there, then you can say, I don't know. So you could do that. And so, yeah, I think you guys have seen this before, but sometimes you see this extra thing here we call a bias or an offset, and that's just to shift things around, but that can just get absorbed into here by making a dummy feature equal to 1. If sometimes you'll see me put it there, sometimes you won't. I kind of mean the same thing in general. Okay, so you could do that. And if we did that, then, so right, you should always also think like, and this is something I see people mess up a lot, not just in this class, but like even like as people get more advanced, is like really learn to think about like, what is the model? And now that I have the model, what is the loss I'm going to use? And then once I have the model and the loss, then what is the training procedure or the optimization I'm going to use, right? These are, each of these is a separate decision, although they're often tied together. If I use a particular model, there may be a particular loss. And there may be also a natural way to optimize it that works well. But these are, right, separate things, and it's good to always make sure that you think of these very cleanly in each case and not mix them together. But so if I had a model like this, so this is producing things of the right type, unlike linear regression, which is on the real value line, this is now giving me basically 2 classes. And then I could say, well, my loss is just going to be to count the number of mistakes, right? Like see what class it was and then subtract it from that. And in this case, if you want to do this, you need to now use whatever. If you were calling a cat and dog, you better start calling it -1 and 1 just so that the math here works out, because you're counting errors, right? Okay, so what could go wrong with this? All right, it's kind of the same thing we saw before, which is it's a step function. It's not differentiable, so we can't get a closed form solution because you can't. That doesn't work, and there's no gradient signal because the gradient's basically 0 everywhere, or undefined. Okay, so that's actually no good. And so the model yields predictions in the right space, but it's not amenable to giving us a natural loss function through which we can do gradient descent, or even just compute the gradient, right? So for neural networks, what we said was, let's use something else, right? Like, let's use a ReLU. And the ReLU looks like this, and then we were like, okay, we're pretty much good to go. There's still some problems, but this is the best thing that works. So can I use the same thing for classification? No? Okay. All right, so this is sort of, in some sense, taking us back to linear regression in a weird way, where I don't have things that lie, it's not going to give me a number that represents the probability of a class, nor does it just give me a discrete number that represents a class. So I made it differentiable, but it's no longer sort of making predictions in the right space, which is a discrete set of labels or probabilities over them, because it gets sort of arbitrarily high. Okay, so what actually the most common thing you'll see a lot in classification is to use the sigmoid, which you also see actually a lot inside at the end of neural networks for the same reason. And so sigmoid is just this function here. So you can see it's almost like an approximation to the step function, right? So in a way, the step function is kind of what we might want, but this is a softer version of it, which has gradient everywhere except when it asymptotes. And it's gonna turn out that that's actually fine for us because we're gonna be working in probability space. So this is almost logistic regression, which is classification. And the only thing that, a reason I'm not saying that it is just yet, is that technically logistic regression is a model, but we always assume a particular loss with it, and so I haven't told you the loss just yet. But just to sort of drive home the point again, like linear regression looks like this, and logistic regression, you pipe whatever that thing from linear regression was you got through a sigmoid, and then it gives you a number that lies between 0 and 1, which we're going to interpret as the probability that it belongs to the first class, let's say. This is all for binary, right? Just for a binary class, and we'll get to what you do for more classes for now. But if I can say that the output of this is between 0 and 1, and I say that that's, say, the probability of a cat, then I can just say 1 minus that is the probability of a dog. Right, so that's kind of what we're gonna do. I'm gonna say, and I'm purposely sort of sometimes changing this out, like this could be arbitrary again, right? This is just class A out of classes A and B, and it's gonna take a linear additive signal, x times a feature weight, and pipe it through this thing, which is a sigmoid, which then makes it go between 0 and 1, which makes it guaranteed that we can interpret it as a probability. Right, and so we have a two-class problem, A and B. And so for binary classification, the way it's going to work is we're going to just say probability that y equals a given xi and some features that we're going to learn is to pipe wx through the sigmoid, and then that's going to be the probability of a. And to get the probability of the other class, we're just going to say it's 1 minus that. And that's fine because the sigmoid forces it between 0 and 1. This will all work out. And then I can just, if I want, I can also and as a consequence, this will also be true by the way I defined it, which is the probability that one of the two classes is equal to 1. So we're good. And so sometimes, so this is now, when you get a prediction from here, this is this thing I said was useful, which is the probability that you belong to class A or to class B. That you can compute both, but you can of course get one from the other. And sometimes if you wanted to, for some reason, say like, well, what's your best guess of a class? Then of course, you just take the argmax over that. So for two classes, you would take the highest one. If you had k classes, you still just take the highest one, and you could say that's my prediction. But in general, to the extent you can use the more nuanced information, depending on how you're using it, you may want to do that. Okay, so here's a thought experiment. Imagine that we're in linear regression, so like the rest of the course, not today, and imagine that we double the weight. What would happen? So that should just say W, I guess. Imagine we double W. Yeah, I need to fix that, not this. I mean, just let's like think through the math, right? It's W times X. If I make it 2W times X, basically all the predictions will get twice as big. So what happens is that the predictions would be twice as large. It was such a simple question, that's why you didn't answer. Okay, what if we did this? We did it for logistic regression. So what if I double the value of W in binary, like logistic regression? So one question, imagine it's binary and it's cat, dog, and I have a bunch of samples and I run them all through. And then I use the rule on the previous page where I just say, tell me the maps. Like, I don't care about the probability, just tell me whether it was a cat or a dog as best as you can. If I double the magnitude of, I take W and I change it to 2W, will I change what gets assigned to be a cat versus a dog? No, I won't. So what will happen is that I'll be more confident. So what used to be actually affecting the scale of the predictions is now affecting the confidence of the predictions because these are probabilities. So the larger the magnitude of W in the regression, the more confident I am about the predictions. So if we now use this logistic regression, then instead of the craft we would have got from linear regression, we will in fact get a line that looks something like this. This is schematic, I didn't compute it, but I should do that. Okay. And as I said, like a lot of the stuff we've already thought about and learned about still applies here, about augmenting the feature space. If you have too many, you can overfit, and I'll show you just a little example of that. If you have too few, you can underfit. You have similar bias variance trade-offs, and the intuition that you've gleaned from that technical analysis you can apply here as well. And there are also these kernel versions which lift you into a different space, and just as you got, and you'll get different decision boundaries. Just as the curve, the regression curve would go from straight to curved if you added polynomial features, here the boundary goes from linear to curved or curvy. And you can also add in a regularization term, so there's sort of equivalents to ridge and things like this. So, but just as an example of what happens, so here, this is a linear model in the x's. Again, this is feature 2 and feature 1. And so, and even though I showed you these nice clean things where the classes are getting cleanly separated, that's actually not how it really works, right? So usually there's a messy, even this is pretty clean. And the goal is I need to find the line as best as I can that is sort of separates these in the hopes that when I deploy it on future data that it's gonna give me a good estimate of the classes. So here I have a linear decision boundary, and you could say maybe that's noise, but maybe it's not the best model. So what if I actually augment this with quadratic features or pairwise features? Now I can get a decision boundary that's actually quadratic, and it looks actually like it makes a lot more sense, right? So it could be that this is actually a better model. And then if I go crazy and I add even quadratic terms here, then I can get this totally like crazy decision boundary. And so maybe now it completely separates the x's and the o's, but I don't think anyone would believe that this is a better model than one of these, right? Like it's just completely overfitting the data. So you get a similar notion of all of these things. Okay, so I've talked about how you get logistic regression using the sigmoid, where you have a parameter and you just kind of decide that that parameter is for class A, and then you do 1 minus the probability of class A to get class B. But what if I have more than that? So this is the example I just talked about. There's one weight vector that gets associated with one class, and then the other class is just the 1 minus the probability of this one. So I could think of this slightly differently. I could say that another way to think about this very same model is that the probability of y given a is proportional to piping the wx through an exponent, and similarly having another weight vector wb and piping it through an exponent, and then normalizing it such that the probabilities add up to 1. And that's what this step here, this says that if I want now the probability, this is just proportional, but if I want them to actually be properly normalized distributions, then I need to add a normalizing factor, which is the probability that it belongs to either, or it's the sum of both of these, right? So this now I can do this for A as I have done here, and if I do it for B, then I just put a B up here and leave the denominator the same. And once I've done that, then by definition, the probabilities will sum to 1, and they will be correct probabilities. Okay, so why am I telling you that? This worked fine. This looks awfully convoluted. So the model will actually be the same, even though I've augmented it with another parameter. But why am I doing that? Because then it makes it much easier to think about, okay, like now I have a parameter per class. Now it's super easy to think about how to do multi-class logistic regression. And so now, again, I say for each class, there's going to be one parameter. For class K, I just call it WK. And the probability that the label belongs to that class is going to be proportional to that. And then I have to add in this normalizing constraint again, which is that the sum of the probabilities need to be the sum of these things. And so it looks very similar to what it was here. So here now, instead of 2 things on the bottom, you just have all the classes on the bottom. So the probability of A will be X with the WA weight, and then all the other ones get added on the bottom so that it normalizes. Again, like you can sit at home and work through to make sure you see how this actually does normalize it if you don't see it right now. And so this is over-parameterized, right? So if I have a parameter per class, as I did right back here, like I know here I didn't need 2 parameters because this is the same model as up here. It just sort of has an extra parameter, and it turns out this is actually a convex function and has one global optimum, and it doesn't matter that I added this because it actually will get to the same place, and you can work through that. And in general, though, you can just get rid of one of these and and do this instead, which is you just say, for the last class, it's gonna be 1 minus all the other ones, which is also what we kind of did when I first introduced logistic regression. So this is sometimes called, sometimes called multivariate logistic regression, sometimes multi-class logistic regression. In machine learning in particular, it's often called softmax regression. And that's because this function that we used is a sort of generalization of the sigmoid. So when I introduced logistic regression, I talked about a sigmoid operation, and it sort of was tied to the idea of having 2 classes. And this is now a more general sort of sigmoid where you can have arbitrary classes, and it's defined like this: is you give it a set of probabilities, so probability for or numbers for each, sorry, not probabilities, like a score, if you will, for each class. And then you say, what's the probability of the jth class? And it is this operation. And this is basically doing that normalization for you that I just described, and now giving a name to it and calling it softmax. And you can verify that it is a probability distribution because it returns values between 0 and 1. And again, you can work through this and see that. And it's kind of neat to just think of how this is a soft version of the max function, right? So normally for max, if this soft thing wasn't here, then the max would just say whatever the biggest one of these is, right? But now it's like actually doing something which is telling you the probability of it according to this function, instead of just returning the max. It's now soft because then you sort of the max and the probability at the same time. Okay, so how will we do parameter learning? So let's just think about the binary example again. So could we use mean squared error as our loss? So nothing would stop us, but it was really nice when we started doing maximum likelihood estimation because it's sort of tied to principles of statistical learning and comes with nice guarantees, which we didn't go over in this class, but you might learn about in your statistics classes. And in particular, when we had this for regression, and we had this sort of ordinary least squares, it emerged, right, from a Gaussian likelihood. And that Gaussian likelihood just doesn't make sense here, because that's for real values with like sensor noise that maybe is Gaussian and things like that, where now we have classes, and there's not really a notion of noise in the class. That would be like a more advanced topic, but there's a notion of confidence in prediction instead. So what likelihood do we have? Actually I packed more into this lecture, so I won't, well, maybe just take like 20 seconds to think about like what likelihood might make sense. So I have a model where sigmoid of W times X is giving me probability of a class. And I had 2 classes. So like what would a probabilistic loss look like that comes from probability? The log likelihood, we want to use the log likelihood, and so the question is like, how is it going to look here? So, right, so it's going to be binomial, basically. You're going to use the binomial likelihood. So before we had a Gaussian likelihood and we did maximum likelihood, and now we're going to use the binomial likelihood. And so that's just, it's going to be, these PIs are going to come from the sigmoid, right? So the sigmoid says, what's the probability that I belong to that one to class? 0, say. And so if I do belong to that class, I want to use PI in the likelihood. If I don't belong to that class, that's 1 minus YI. So YI are like real targets here, right? That's the label I have from my data. So I'm either a 1 or a 0. So if I'm a 1, this term turns on, and this term turns off. And if I'm a 0, then this term turns off, and this term turns on. And I'm also picking up whether I'm probability, right? PI should be probability 0, 1, I guess, and the other one the other way around. That's 0. Right, so that's the 0 class array, and that's the 1 class. Okay. Right, and so how you set this up here will depend on whether you've decided to call this class 0 or class 1, because you could tweak it the other way around if you wanted to, but that would be kind of weird. And right, so the log likelihood is you're gonna sum over all of your data points, and we're gonna just take the log of that, right? So when we take the log, then these exponents come down, and so now I get something that looks like this. So we are again doing maximum likelihood, but it's not like, it doesn't look anything like the Gaussian maximum likelihood, right? It's because it's using a binomial. And then I sum up over each data point, and so, but you can think through, like, what is this doing, right? So imagine for one data point, yi is a 0, and so here this term falls out, so this doesn't hurt me if I'm minimizing. Is this minimized? Oh, no, that's still positive. So I want to maximize this. So but in any case, this term will fall out if y is a 0, and if y is not a 0, it's a 1. So this, which way? Sorry, I'm getting messed up. So if it's a 1, this term is on, and then it pays attention to pi, right? And then if it's a 0, then this term goes off, and this one turns into a 1, and it looks at 1 minus pi. And so this is essentially the analog of a Gaussian, but for classification. And it's really just saying is like, if I was a cat, and you gave me a high probability of being a cat, then I'm gonna have a higher likelihood. And if I was a dog, but you gave me a high probability of a cat, then I'm gonna get a lower likelihood. So that's basically what this is doing. And then the game is gonna be that to change the W, right, to maximize this thing. It's the same principle, is to do something like gradient descent. Any questions? So right, this is the simplest classifier, which I said before. And then you get this question of, okay, well, how do we estimate the W? And one of the reasons we chose the sigmoid is that we can get gradients through it, and so we can't do it in closed form, as it turns out, and so we're again going to use an iterative procedure. And again, you could sit down if you want to convince yourself and try to get a closed form solution and see that that's just not possible. And so, right, so you can go step through step and take the derivative. So if the loss is a function of W, and we're trying to learn these parameters W, we're gonna actually, typically we take the log likelihood, and then sometimes we minimize the negative log likelihood. So that's actually what's written here, and this is just sort of copying from the previous slide. And we want to take the gradient of that loss with respect to W. So just take the gradient, just putting this whole thing in parentheses, putting the gradient term in front. Then I push the gradient through, and I push it through the summation sign. That's all that's going on through each term, right? So the gradient suddenly is now in here, and it's with respect to W, so I can push it past yi. Y is just my observed label. And remember, W is inside of P. That's where the W is. I'm going to keep this up here so you can remember that. And so again, I push it past the stuff that doesn't have a W, and then take it the gradient of this. And I can keep going like that, and now I just apply the rules of taking derivatives of logs, and I get 1 over pi times the gradient of pi, and similarly here. I can work all the way through, and then I get a term that looks like this. Okay, so then I'm going to continue on the next slide. This is just the last line from the previous slide. Right, so what I'm going to try and do is reduce this a bit further. So P, remember, is the sigmoid here. So what does the gradient of the sigmoid actually look like? It looks like the gradient of this thing, which is the gradient of that, which is this, which is that. And I know it's fast, but like you can see, but what's really cool about the sigmoid, and this is like a well-known fact, is the gradient of the sigmoid is the sigmoid times 1 minus the sigmoid. So that's like kind of funky and neat. But so that's helpful. So we can now plug that in. So this is what we had, and what we just showed is you get this really nice term for the gradient of P. So So I'm just now plugging that in. That's the sigmoid times 1 minus the sigmoid. And then, of course, I have to apply it inside the sigmoid, right? With respect to W, that's where this x comes from. And so now I get this, and, right, moving the math around. And in the end, I get actually, after all that, I know it's a little fast, but you get this really nice term out like this. And so actually, and you can write this in vector form, so the gradient of the whole vector of W in logistic regression is just looks like this, which is kind of neat. And so we can, in fact, do gradient descent. And there is no closed form solution for this. So we're gonna just, again, do the same stuff we learned about sort of 2 lectures ago, and with some step size here. But, and I mentioned already that this is convex. And so because it's convex, it doesn't matter so much how we initialize it. It doesn't matter as much how we change the step. Like in principle, if we do it roughly correctly, we'll always go to the single global optimum. And so how could we check that? It's always good to know how to check these things rather than just have me tell you. So if the Hessian of the loss is positive, I mentioned this before, is positive semi-definite, then the loss is convex. And so you can go through and show that. So the Hessian is a matrix, right? So it has a KL term, and the KL term is going to be the derivative with respect to WL and WK. And recall that we just spent a slide going through what the actual gradient is. So that's the gradient from the last slide, and I can make use of it in the Hessian, right? Because I'm trying to get second derivatives here. So now I say take that result I had from here, that result was this nice simple thing, and just apply the second derivative to it now with respect to WK. And then when I do that, then I get this out. So right, the yi disappears again because there's no dependence of W on the y's, and it just comes out of here. And then of course the derivative of the p again brings out another x, okay? And right, so the Hessian at the end of the day, like this is the KL element of the Hessian, and if I put them all together, then it looks like this. And to prove that L is convex, then I need to show that that Hessian is positive semi-definite, and there's different definitions of that. One definition of that is if I take any W and multiply it by the Hessian and then again by itself, it has to be greater than or equal to 0. And you can show that pretty easily here. So you just take the Hessian we just computed, which was this thing on the previous slide, pre-multiply by W transpose, post-multiply by W. And when you do that, you get something that you see, like, remember, PI is between 0 and 1, so this has to be between 0 and 1, and this is an element that's squared, so it has to be greater than or equal to 0. So altogether, this has to be greater than or equal to 0. So what we've just shown is that this value is always greater than 0. Because this value is always greater than 0, it means our loss, it means that the Hessian is positive semi-definite, the Hessian of the loss, and because of that, the loss is convex. Because the loss is convex, then it has a single global optimum. And so that means these are like really, really easy to optimize. Right, okay. So now we have this multinomial likelihood, and we sometimes call this multinomial regression as well. This is all kinds of different names for the same model. And if you want to generalize that binomial likelihood, then it looks almost the same, right? So instead of breaking it up into was y equal to 0 or 1, now you just have something like, does y, this is an indicator function, is yi equal to k? If so, then keep this term, and if not, don't keep this term. And then you just sum over all the classes. So in binary, we didn't have a sum over classes here because we just wrote out for class 1 and then class 2. But now with this sort of new way of doing it, we sum over each class, and only the one for the class it belongs to will get kept, right? Any class that doesn't have that label, it will ignore the term for that. So this is picking off only one class per data point, and this is summing over all of the data points here. Right, and so PI is the softmax picking out the kth softmax from the set of these WX's. So intuitively, again, the way you can think about this is each class has a W vector that gets learned. So what you do is for each class, one at a time, you take that vector, like once it's been trained, for example, and you multiply it by X and you get a score. And in some sense, the higher the score, the more, and it's not a normalized score, right? Because Wx is just on an arbitrary line. But when I pipe it through the softmax, then it now gives me a probability. And the way intuitively in which that's going to happen is the larger W times X is, the higher the probability of that particular class relative to the other classes. And so the likelihood, again, is similar. The log likelihood is very similar to before, except instead of breaking it out for binary into like the yi and 1 minus yi, we again just use this indicator trick where this thing evaluates to 0 or 1 only if the yi is equal to k. So it's basically the same thing, just a bit more notation, and maybe not quite as maybe intuitive, or maybe more intuitive. Right? And so the rest is analogous to binary case. So it's also a convex loss, and you can also take the gradient and all of these things. Everything just happens in the same way. Okay, so I mentioned in the beginning of this lecture that the shape of the decision boundary is what's like really important, right? And that the more complicated that shape, the higher capacity a model we have. So, and I also said that the way you get what is this boundary, like as I said, we're not gonna necessarily just like kind of think about it intuitively, right? So if we think about logistic regression, it's hard to think through like what is the boundary. It's easier to say, well, the boundary, the definition of that boundary is when the probability of each class is the same. So let me just write that down given this model, and that is, right, so when probability of this thing, of A is equal to B, like when those are the same, that's gonna give me some sort of boundary. What does that boundary look like? So I can just write it out. It's when this is equal to this, because the normalizing constant will cancel. And now that's basically like a level set, which is a line, right? So if I solve for this, it looks like this. And this is linear in X. So I get essentially a linear decision boundary. And you can see that if remember I said this was over-parameterized because there's a W and a and a WB, you can rewrite it with just one, and then you would just get the one weight there in the end, basically. It would look similar. But the idea is that you take some model, and it's not, you don't always know what the decision boundary looks like. Maybe as you progress, you might have more intuition, but what you want to just sort of crank it out algorithmically. You set the probabilities equal to be the same, and then you you look at what that equation of X is. And if it's linear in X, it's line. If it's quadratic in X, then you have a quadratic decision boundary, and so on and so forth. And we'll see more examples of this. This is just sort of one introduction to this topic. We'll see more, I think, in the next lecture. Right? So, but this is a linear boundary in features in X. Okay, so, and then we just have a couple of more slides. So when I introduced neural networks, we haven't got to classification, and I said you just use a linear layer at the last level to do regression. And similarly, if you put a softmax layer at the end of a neural network, this is how you get it to do classification. This is the very, very standard, common way. I don't think anyone does anything different. There are all kinds of things people change about neural networks, but this, I'm unaware of anyone who does something different than this at the last layer if they're doing multi-class classification. So, and again, you can, right, so in some sense, classification and regression are very similar. All that other stuff could be the same, all the convolutions, all the pooling. And the thing that changes is that last layer. Is it a softmax or is it like a linear layer? And it also, what it also shows you is that actually a neural network can be interpreted as a probabilistic model. And so what loss would we use now? We could use, sorry, the animation is screwed up here, but okay, I don't know let's see what surprises me next. Okay, wow. Right, so we can actually use the same loss I just described. And you're like, wait, how can I do that? This is a totally different model. It's because I've hidden all the details in here, right? So in logistic regression, PI was the sigmoid of WX. Now PI here is just whatever the whole neural network computed, basically, and then threw a sigmoid at the end. So I'm just hiding it in the notation, but fundamentally it's actually the same loss, and we can also do back propagation through here as well. Well, okay. Right, okay, so one last thing, is that you often hear people say, I'm using, maybe you haven't, but you will one day, as you go on, you'll be like, oh, I'm using a cross-entropy loss, or you'll install scikit-learn or TensorFlow or something, and it'll just be like cross-entropy loss, and you'll think, like, why did they teach me maximum likelihood? What is this cross-entropy loss? And so it turns out they're actually one and the same, and it's unfortunate that many people now don't know that they're the same, and so you don't need to worry about it, it's fine to use. And so there's some slides here showing how you can do that. So, and sort of the starting point, and this is something called the Kullback-Leibler KL divergence, and this is a very common beast from information theory, which we're not gonna do any information theory here, but it pops up all the time in machine learning. And it's because it's measuring, in some sense, a distance, if you will, between two distributions. And so why is that important? Well, you can imagine, in some sense, when we want to fit a model, we're trying to say, how well does a model fit my data compared to the true distribution, where all we have about the true distribution are the actual training data. And so in some sense, it turns out, when you're doing maximum likelihood, you're actually minimizing the difference, the Kullback-Leibler divergence, between your training data distribution, implied by the training data, and your actual model class. And you find the parameter setting that minimizes this. And it turns out so actually minimizing the KL divergence is the same as maximum likelihood, and it's also the same as the cross-entropy loss, which if you go through, we can see. But this is the basic definition. You'll probably, if you stay in this field at all, you're gonna see this a lot. If you just happen to pull out some of my most recent papers, this is all over them as well. And you can see though that it's not a true distance metric because it's not symmetric. It's not, you can't just flip P and Q around, so it's not technically a distance, and the reason it's commonly used is it's actually computationally very tractable, and still gives us a lot of what we would like. And you can just see by looking at the form here that it's not symmetric, right? If I switch P and Q around, this is not gonna give me the same thing. And so it has some properties like it's always greater than or equal to 0, and it's only equal to 0 if the two distributions are the same. So if you can drive your KL, if you can find a parameter setting that drives the KL divergence between your estimated model and your training data to 0, then you sort of somehow exactly captured the training data, which you might not want to do because you could actually be overfitting, but it gives you just an intuition. Right, and it's used all over modern day machine learning, so we're not going to go into these things, but there's some fancy ways to estimate parameters when you can't do maximum likelihood, and something called variational inference. You might have, if you're sort of a hobbyist machine learning person, you might have heard of variational autoencoders, also used there. And later in this class, we're going to learn about the expectation maximization algorithm. It's going to come in there, So, but now I have a few slides that just shows you how is maximum likelihood and cross-entropy and the KL divergence, how are these all kind of tied together, and how are they the same thing? Except we're out of time, I guess. There's only a minute, so maybe I'll just quickly finish this up next lecture before I start, but I'll post it all online today. Okay, thanks.